Hello and a very warm welcome on behalf of NTI Audio. Today we are talking about sound propagation, which is a huge topic. We could talk about that for hours and days about all the effects and side effects of sound propagation. So what we had to do, we had to restrict ourselves to a couple of key themes, key issues, which are listed here. We will start with the issue of sound generation, the differentiation between near and far field, followed by some words about the wavelength. Then we will present some information about directional characteristics of sound sources, as well as reflections and damping. We have also prepared a practical presentation for you, which will be wrapped up by a summary of the key issues that we have presented in this presentation and some comments on questions that have come in. I expect the overall duration of this presentation in the range of about half an hour. My name is Markus Becker and I'm assisted today by Sven Müller. He is mainly taking care of your questions and answering to them. This is just an example, a room, a concert hall, where you might be responsible for the PA installation. It's an example to show how important it is to understand the different aspects of sound propagation in order to cope with the corresponding challenges properly. And we would like to start with the starting point anyway of sound generation, and that is the sound sources. What is happening in a sound source? This is just a very rough explanation, a rough visualization of what is happening. Let's assume you have a drum which you are beating. So you have a membrane which is deflected in both directions, and in that way it is generating a sound. Well, what is happening actually? Let's imagine we have a piece of air, a slice of air here in front of that membrane. So as soon as we beat the drum and the membrane is deflected, this slice of air will be pushed and dragged forth and back. Well, this means the air is moving, and it also means that the sound waves are created by that, the sound pressure waves. However, there are many more effects happening in here. For instance, because any membrane or string in a guitar is limited, we have a rim of that membrane, for instance, and at that rim there are special effects happening. Then furthermore, the membrane is not deflected ideally as a flat surface, it is deflected, it is warped. So all these effects together end up that the sound field in this very close area to that membrane is inhomogeneous. Inhomogeneous means that if we would place a measuring microphone in here, we would measure a certain sound level and we would move that microphone a little bit, we would get a completely different result due to the inhomogeneity. So this area very close to this sound source, we call it the near field. And in the near field we are noticing air movements based on the movement of the membrane in that case, and also sound pressure waves that are created. But altogether gives us an inhomogeneous field, by the way, especially at high frequencies. You will see that on the next slide. Well, as soon as we go a little bit further away from that membrane, we have a different situation, because here the movement of the air is no more noticeable, but what we see are the sound waves that are propagating through that area. So we have changes of crest waves and the opposite, the sound waves are propagating through that area. And that means that here we have a homogeneous situation. In opposition to the near field, the far field, that is where we are talking about, offers us homogeneous situation. So the sound pressure waves are moving through that far field in somehow standing air. This is a rough but basic explanation. What's the difference between near field and far field? Coming back to level measurements, you should always prefer to do these in the far field, so in a sufficient distance from the sound source in order to have homogeneous, consistent situation. This is just another terminology how we could call this difference. It's the presence of interferences that makes a difference between the near field and the far field. Well, if we look at the border, which is of course not a sharp line, it's more a kind of a transition area, the distance from this border from the sound source depends on various parameters. It depends, as mentioned before, on the frequency or the wavelength. Wavelength and frequency correlate to each other. I'm going to show you that on the next slide. It also depends on the transducer size, the diameter of the transducer, or of the number of transducers. Here, for instance, we have 2 transducers, so we have to add up the overall diameter of these transducers. Or if we have a surface that is reflecting the direct sound, which again adds up to these interferences, that has to be considered as well. So the correct calculation of the near field, the size of the near field, is pretty demanding, it's pretty complex. I want to show you here just a basic rule of thumb, which says that the minimum distance you should consider from the sound source would be in the range of the diameter of the loudspeaker, or the joint diameter of all loudspeakers squared and divided by 4 times the wavelength. In practice, I'm going to give you some few examples. For instance, calculated for a transducer of 20 centimeter diameter. Here you can see that for low frequencies, 20 Hertz, the near field is very small. It's just a fraction of a millimeter. Whereas for high frequencies, we have a noticeable size of the near field. On the last slide, I introduced the parameter wavelength, and actually the wavelength is a key parameter for most effects that are related to sound propagation. So it is very important to properly understand what it means and to get a kind of a concrete idea of in what range the wavelengths are in the audible sound range or audible frequency range. Wavelength is defined as the fraction of the speed of sound divided by the frequency of that sound. Just remember, the speed of sound in air is about 340 meters per second at 20 degrees centigrade. So how do we get the wavelength, or how can we imagine the wavelength? Let's assume we are again in the far field. We have a sound wave propagating here. Now we could plot the pressure, the sound level pressure in that far field, and by measuring the distance between the wave crests or the wave troughs, then we would get the wavelength lambda. And here I have plotted a number of examples. Maybe you wonder, why did I start at 1 Hertz? Because we cannot hear that anyway. But the nice thing is that it's kind of a memory hook. At 1 Hertz, the wavelength is 340 meters, which is the same figure as the speed of sound. You see here the 340. So if we multiply the frequency by 10, if we look at 10 Hertz, we have 34 meters. Or 1000 Hertz, 1 kilohertz would be just 34 centimeters. And you see the audio range, 20 Hertz to 20 kilohertz. For that audio range, the wavelength is between a couple of meters and some very few millimeters. That is the range that you should keep in mind because it plays an important role for many effects that I'm going to show you now. One effect, for instance, is the directional characteristic of the sound source. Ideally, we would prefer to have point sources which have a perfect, homogeneous, spherical sound radiation in all directions. However, in reality, we can achieve spherical sound radiation, but in most cases, it's more a cone. And the actual shape of the directional characteristic depends on the wavelength and again on the size of the transducer. Let me show that in a few examples. Here we have a transducer where the wavelength is clearly smaller than the diameter of that transducer. And consequently, the directional characteristic looks like a pretty sharp cone. This is typical for high frequencies. Mid-range frequencies, where the wavelength is about the same as the diameter of the loudspeaker, have a wider cone. Whereas basses, where we have a very high wavelength, much bigger compared to the diameter of the loudspeaker, have a kind of a spherical radiation. Well, if we look at a concrete design of a three-way speaker here, for instance, you will notice that the high and the mid-tone speakers have been installed in a specific shape, in a cabinet with a specific shape. And the reason for this shaping is that we want to achieve a controlled coverage of the sound field. We want to achieve a consistent frequency, which is not only on the axis, but also aside of or not only here on the mid-axis, but also in all that, in the whole region here, we want to achieve a consistent frequency response. The woofer, however, you don't see any specific shaping here of the cabinet, and the reason is quite simple, because as showed here we have anyway pretty spherical radiation. Another effect that is related or depends on the wavelength is the question whether a sound wave that hits a surface, a rigid wall or a glass, whatever, how it will be deflected. If it will be reflected in the same angle, that happens if the wavelength is larger than the structure of the surface. So if it's a pretty even structure, we will have in most cases a reflection. However, if the structure of that solid surface has a shape that has comparable dimensions, like the incoming sound wave, the wavelength of that incoming sound, then the reflection will happen in all kinds of directions, so we will have diffusion. And the reflection, this case here, is very important indoors, because here it may happen that if we place our loudspeaker or sound source in opposition to a solid wall, then we will probably face what we call standing waves or room modes. And that means that the waves that are emitted here and reflected by the wall will come back to our sound source and go into resonance, for instance. So the consequence will be cancellations of the sound wave, superpositions. And that happens if the distance between the sound source and the wall is a multiple of the wavelength. Unfortunately, these standing waves are causing a lot of audible imperfections, of annoying effects. For instance, this comb filter effects, you may have heard of that, are a typical consequence of these standing waves. Let's assume we are emitting here a nice flat frequency response pink noise, then you would measure at some points here these awkward frequency response because of these cancellations or the superpositions of the standing waves. Well, how can we avoid that? First of all, we could of course change the geometry of the room, the distance or the direction of the loudspeaker, or the other option we have is to damp the sound waves that are hitting the wall. Damping means ideally we would like to absorb the incoming sound just to avoid that anything will be reflected. And for that purpose, we have to apply a damping material. And this damping material has to be at least a quarter of the wavelength thick. Why quarter of a wavelength? Because just if you imagine the sound hitting the surface here and now propagating through it, and of course it will be reduced in its amplitude, but still a certain portion hits the wall and will be reflected. So the whole path from here and back and forth, we will achieve half of a wavelength. And by having an overall distance of half a wavelength, we will cover the maximum sound wave velocity, and that means we will achieve the maximum damping effect. Well, if you remember, we had these low frequencies with wavelengths of a couple of meters. It will be pretty difficult to design such an absorbing material with a thickness of several meters to absorb the low frequencies, this is hardly feasible. Fortunately, there are some other solutions. I'm not talking about the foam now. We have mechanical solutions, for instance, the Helmholtz resonator. Unfortunately, the description of that would go too far. It would boost the scope of this webinar. But just for your information, there are some nice solutions for damping low frequencies with reasonably sized elements, mechanical elements. Another effect I would like to mention here is the shadowing effect. If we have an obstacle in our room, so the sound waves are hitting that obstacle, what happens? The answer is it depends on the size of the obstacle. If the obstacle has about the same dimension as the wavelength, you will hardly notice anything. It is kind of transparent to the sound, to the incoming sound. However, if the obstacle is larger than the wavelength, you will have a region behind the obstacle where the sound field is definitely changes. We have a lower amplitude in here, a lower level. Then the larger the obstacle is, the larger is that region behind it where the sound field is has a noticeable difference. Another question that is frequently asked is the relation between the level and the distance. So by which amount decreases the level by if I go away from the sound source? Well, in an ideal situation where we have a point source in a free field, we would say that doubling the distance would half or cut the level by half. So the level is inversely proportional to the distance. R is the distance from the sound source. So doubling the distance would mean minus 6 dB in the level. However, in reality, sound sources are in most cases not point sources, but for instance, line arrays. The soil, the ground has an influence, whether it is, for instance, concrete or lawn or grass has a different effect. So this direct relationship here is in many cases, in most cases, compromised. Even indoor, it's even getting worse because here we do not only have the direct sound, but we have also reflections from the walls, from the floor, from the ceiling, and so on. So for that reason, it is difficult to exactly predict the decrease of the sound level versus distance in the reality. Of course, you can measure it. Well, I'm here at the point of my practical presentation. I have here on my desk an EMMA Pro signal generator that is driving an active loudspeaker, and I will be able to turn that loudspeaker on its axis. You will see that. I have an XL2 that is connected via USB link to my PC so that you will be able to watch the screen content, the measured values of the XL2. Let me activate that. And in addition, I have also prepared a small webcam here so that you can see what I'm doing mechanically here on my desk. I'm going to just activate it here. So here you see I have a microphone and I have my loudspeaker which is pointing towards the microphone. I'm going to now activate the sound, which is a sine wave of 40 Hertz. You can see that down here I have a 40 Hertz tone, which is in the range of 73 dB SPL. Now I'm going to turn the loudspeaker away from the microphone and please watch this number, watch this sound level. You have noticed there's almost no difference. The sound waves from that bass, from that woofer, the level stays the same, and the reason is, as I said before, because we have a spherical radiation. Now, if I change the frequency of my signal generator to, let's say, 8 kilohertz, I'm going to do the same. And here you noticed there is a tremendous difference, about 20 dB, between the situation where the loudspeaker is pointing directly to the microphone or where the loudspeaker was pointing away from it. That is exactly that effect of the directivity of for the high frequencies. I'm going to show you now another effect. I'm using a cardboard which I put between my microphone and the loudspeaker. And you notice as soon as the cardboard in between, the level drops, and this is this shadowing effect that I also mentioned before. Now, as soon as I would reduce my frequency back to 40 Hertz, and I do the same, there's nothing visible, no effect, no change is visible. And the reason is very simple, because the wavelength of the low frequency is much bigger than the size of my cardboard. And for that reason, the cardboard is transparent, it's invisible in the world of sound. I want to show you this effect also by looking at the spectrum. I'm going to now create a pink noise signal, a wideband pink noise signal, and then I will turn away the loudspeaker, and you can watch what happens to the spectrum when I'm doing the process of turning the loudspeaker away. I guess you notice that these bars here at the low frequencies stayed almost unchanged, whereas the bars at the high frequencies slowly dropped proportional to the position of the loudspeaker. Well, let me get back to my presentation. And summarize what I have shown to you. First of all, keep in mind the most important parameter for sound propagation effects is the wavelength of the sound. It tells us about the directivity of the sound source. It allows us to properly design damping materials because we want to avoid reflections. It allows us to assess whether an obstacle in the sound field would act as would cause shadowing or not, just by considering the size of the obstacle and so forth. And I have also once again listed here these typical lambda wavelength values, starting with the 340 meters for the 1 Hertz signal, just as a memory hook for the other values, from some meters down to few millimeters in the audio frequency range. Remember that the far field is the homogeneous part of the sound field in front of a sound source. This is the part, this is the area where we should place our measuring microphones and just avoid the near field due to its inhomogeneity. And last point, when you are working indoors, inside, obey that indoors we always have to cope with reflections, and we have to cope properly with this challenge in order to achieve a homogeneous, consistent sound field for our public. Well, I'm at the end of my presentation. At this point, I would just like to point out that if you have any other issues, other questions, or if you need support, please do not hesitate and contact us or any of our subsidiaries or partners that we have worldwide. These are just the list of subsidiaries here that we have, and down here on that website you will find all the partners, the independent partners that are supporting or selling our products worldwide. I hope I was able to answer most of your questions, and I'm looking forward to meet you again at one of our future webinars, which we will announce as usual via our newsletter. Thank you for joining me, and have a good day. Bye-bye.